Okay, so hello, welcome to everyone to episode 1 of Talking Shop with Tony Abbey, what we're hoping to be a new regular series, looking at a different technical topic each week, featuring a mix of discussion and comment and feedback from you guys, the audience. My name's David Quinn, editor of NAFEMS Benchmark magazine, and I'll be hosting things today from Glasgow in Scotland. So this week, Tony, who's over there in Knoxville, Tennessee, he'll be looking at St. Venants Principle. We'll kick off with a presentation from Tony and then open things up to your questions and comments. But without me wasting any more of your time, I'll hand straight over to Tony and we can get started. Tony.
Thanks very much, David. So basically this is all about St. Venants Principle. And I've got two confessions to make straight off the bat. The first off, I described this in the promo video as St. Venants Theorem, and I guess for over 40 years I've been under the misunderstanding there's a theorem and there's a principle. The theorem is actually quite complicated about torsional and circular shafts. The theorem is actually quite a kind of a loose thing. The principle is quite a loose kind of definition, as we'll see a little bit later on. Also, the second thing is I do apologize to all French speakers. My pronunciation of, I'll try it once very carefully, Saint Venant. When I'm in a live class and there's somebody who's French speaker, somebody who's French, they always pulling me up on this, and I try and remember. So that's my best shot there. It will now degrade as we go into the presentation. So what is St. Venants Principle all about? Well, the translation that I found is this, a lot of wordy stuff. The difference between the effects of two different but statically equivalent loads becomes very small at sufficiently large distances from a load. A, that's a real mouthful, and B, it doesn't really kind of tell us what, how can we use it? What's the principle behind it? And that's really what I want to kind of explore in this session. And again, these are just my ideas. You may have different ideas. And again, I really welcome any feedback, any, Tony, that was rubbish, that's wrong, I don't like that. Oh, that's a good idea. Whatever it is, please feel free. It's again, it's a discussion, perhaps more than kind of perhaps a teaching. So what it means is that I've got two plates here, and I'm applying a load at the far right-hand end. This one, I'm applying a point load, but my target region of stresses is over here, where the yellow circle is. And basically what St. Venants theorem is saying is if the applied load is far enough, we don't care what the form of the loading is. Now, they must have the same equilibrium at the center of the target there, so the forces and moments must be the same balance. So we have fundamentally the same load path, but basically we get this diffusion effect coming in. So the local stress state is insensitive to the form of loading, and that's something we really leap on with finite element analysis. I'll try and show some examples of how we kind of take advantage of that kind of as we go through. So that's the idea. Let's actually put some stresses on there. Now here I'm looking at the stresses flowing in this plate in an axial direction, and what I've done is I've clipped the contours. I often do this in FE analysis. I don't want to have some crazy high number here and then everything else scaled down to that. So I've clipped everything at 1400 units, I'm going to call it. The loading I'm putting on is 1000 units. There's cross-section areas unity. So the nominal stress is 1000. Nominal stress is sort of this kind of mucky green color. So we're over here, we get the nominal stress. So this was our target region. We can see we've got diffusion back to the nominal stress at that point. Again, it's a bad idea to apply a point load, so this is something we wouldn't typically want to do in an analysis, but just really to show the point. And just to emphasize, this is a stress singularity. The stresses go off to very, very high levels here, which we'll kind of show shortly. One quick word about the boundary condition on the left-hand side. I've constrained here in the x direction in translation, and then all the rotations, but the y direction, I've only put the center line point constraint on, or a single node there. That allows free Poisson's ratio contraction, so I can get an even stress distribution. If I don't do that, then I grab this end, or grab the edge, and I get singularities popping up here and here. So just a little tip, if you want to emulate this, I want to repeat this kind of work, then that's just something you have to pay attention to. And here is the distributed loading now. So I've used this, and I've got to thank the folks at Siemens. They actually allow me to use their products here, FEMAP and NX Nastran. on a kind of a gratis basis as I do this, and various other solvers, other FEA companies do as well. So I would like to thank them for that. This is an even distribution of load applied here, so we're getting a good distribution of stress right on that edge there, so naturally there's no issues back in here. So basically, that is the bad news. This is the good news. This is the distributed load in here. So that's what we want to look at. Now, I've played some variations on this. I've said, well, let's put corner loads on, or on the center load. So really trying to sort of emphasize the point that whatever happens in our target zone, it doesn't really care too much what the loading form is there on that right-hand edge. I've split the load here corner to corner. You can see the blue here, and the way I've chosen to represent the stress is that zero stress. So you can see that stress diffusion and stress flow. And I really like to think about stress flow. We can think of it as like a potential flow. And there are some analogies to fluid flow. It's like an airstream, not completely, but you know, at least we can begin to think of that. So sometimes I like to think of stresses as flowing. Now it's only the x component, but nevertheless it gives us some kind of idea here. We're getting two singularities. We're getting a diffusion length, which is again dominated by these two singularities at the corner there. And I carry on playing games. Now I split the loading into three, and now we've got three singularities, and the diffusion is still it's about the width of the plate, notice, that we get our diffusion length over there, and I'll come to that point in a minute. Now I put 3 points, there's 3 blips, 3 singularities. Now I've just split the load to a third across here, and again, a little bit of an aside, that's something that we wouldn't want to do, because what happens is that the edge stiffness, the element on the edge there, or node on the edge there, is only, if you like, connected to one element. In the middle, that node is connected to 2 elements, so it actually has twice the stiffness. So what we do there is we actually double the load in the middle, because we've got twice the stiffness, and we halve the load on the corners because we got half the stiffness. We can't really see it here, but if we actually put little point forces all the way across here, which is not a good idea, we would drop the load at the corners by half, and then we'd actually get back to a good distribution on that edge there. Little points which are coming out as a side, but again, they're useful to kind of pull out. So this is perhaps the bottom right is the best effort we can do with these point loads in here. But again, even then, that diffusion length has got a little bit better, a little bit shorter, but it's still about the order of the width of the plate. So we're playing around different types of application. Now I got a little bit more formal. What I've done is I've split this plate up. So this is the center load here. I want to know, well, I always think of a contour plot as being like a subjective plot. We can get the idea of what's going on. But I like to look at XY plots to get a more objective view of what's happening. So here, what I'm doing is to plot on the right-hand side here the stresses at different stations. So the pale green here, I've called it the edge, this is the singularity, and even with the very fine meshes I have in here, it just can't handle it. The numbers are crazy, and we go and we shoot off, and I can't remember what the peak value is here. It's probably about 30,000 PSI I'm quoting here rather than the nominal 1,000. So the blip in here is enormous. If I let that contour rip and get it to go to its maximum value, it would just be a red dot in there as we reach the singularity. We're not interested in that today. What we're going to say is, well, the edge there, we know it's ridiculous stress distribution. Come in 2 inches in, and that's about, this is actually 10 inches wide and I think 20 inches long. So we're coming at about this station here, and we can see, okay, now there's some semblance of a diffusion. But notice it's to 0 here, peaky in the middle, which is what we see through here. And the idea is that we get a diffusion length, and here the diffusion length is just around about 10 inches. So the gray dots across here are showing that 10 inches, so that's kind of equal width, kind of just about here. We can see a little bit of a variation if we look at the contour bands. We look at the plot across here, but it's headed towards the nominal stress of 1,000. And by the time we get here, there's a couple of contour flips, or there's one contour flip here as it kind of goes 9995 to 1005 maybe. but there's, to all intents and purposes, we've got a nice settled stress in here. So that characteristic length seems to be associated with the width of the plate in that particular case. So the stress becomes more or less constant after that distance. And that's what some Venants, he can kind of quite pick up on a characteristic length, but we tend to notice that we have this idea of characteristic length. And that's something I really want to kind of jump on and talk about kind of as we go through here. So now I'm going to narrow the plate and see what happens. Well, as I narrow the plate, it's interesting. We still get the stress singularity here. But now, if I look to see again, there's the singularity on the edge, 2 inches in, 4 inches in, 6 inches in. By the time we get to 6 inches, it's smoothed out beautifully at that particular point. So again, this is now, the plate is 5 inches wide. So it's actually about 5 inches is where it settles down. Somewhere between 4 and 6 inches, we actually get a good diffusion settling down. So it seems to be telling us is that the trend is the plate width is related to the diffusion length, and we'll keep on looking at that as we come to the next slide. I've narrowed it even further, so now it's just the width is just 2.5 inches. So we can see that the stress flow, and I've kept the nominal stress the same. I've reduced the load as I reduce the width, so I keep this 1,000 nominal. You can see with the cuts I've got, or the lines I've got, it's diffusion very quickly. So everything overlays on top of each other after around about sort of 2 inches. We see 4 inches and beyond is nicely sitting down on the 1,000 level. So the stress is constant after, again, what looks like a critical distance for this idea of some Venants principle. It's something physical that we can perhaps pick up. We can use an engineering judgment call. It looks like it's actually the plate width in this particular case. And I think that was the last one that we do in the series there. So just some conclusions from the plate example. Point load is a bad idea, but I'm doing it here to show the principle in practice. Please don't, I'm always careful to say, I'm using this as a demo, but don't do this at home. Basically, don't apply a point load. Bad news. The stress diffuses to a constant over a certain length of the plate, and so it looks like this diffusion on characteristic length is a function of the plate width. In this particular case, with this particular geometry, it's not a function of plate length. Now, why is this? Well, the edges of the plate act to align the stress locally in an axial direction. So as that plate gets narrower, the stress is already entrained to flow tangential or parallel to the edge of the plate. It's a little bit like fluid flow. If I've got a wind tunnel, and it's a very big wind tunnel, and I've got a small feature in there, then the air is kind of coming up to that feature and having to diffuse around it or move around it in quite an abrupt way. If I have a narrow wind tunnel, or the object is occupying a large amount of space, then the flow is entrained along the walls of the wind tunnel. So it's not a surprise. The flow is already moving parallel, and then it sees the object and it is going to change its direction a little bit. So that's why putting a large object in a narrow wind tunnel isn't a good idea, because you're not modeling free stream flow. So this is the idea. The narrower that plate gets, the more it's entraining, and it's actually keeping that critical plate length, the critical length to the plate width. So the narrower plate actually improves the stress flow. It diffuses to a constant level faster. We see that effect in the stress concentration factor calculation. If we've got a plate with a hole in it, then if it's an infinitely wide plate, we can say the stress concentration factor is 3. Actually, it's then we bring in a finite width plate. As that plate gets narrower and narrower, the stress concentration factor actually goes down, because it's exactly the same idea. We're constraining that stress to flow. Now, the counter to that in stress concentration factor is that as we narrow that, then the nominal stress goes up. So we've got stress concentration factor of 3 times perhaps a low stress, and then we have a stress concentration factor perhaps has dropped down to 1.5, but the nominal stress has gone up because our net section is bigger. But it's the same kind of idea, same kind of effect. So something to kind of think about. I like this I like to think about stress flowing and the way that the stress flows. So stresses tend to diffuse to nominal values at distance from the local stress raisers. That's, or local loads, I should say, is the key thing that some Venants picked up. But we can also say, obviously, the same thing if I constrained one edge as a point, then away from that constraint, same kind of idea. So loads and constraints are really what some Venant's talking about. He's actually talking about loads, but we can talk about constraints. But I can also extend it to local stress raisers. We have a disruption of the stress flow in a local feature. As we move away from that, we get the same kind of effect. So some Venants didn't really talk about that. I think common sense, we can apply the idea to stress raisers. These are all generally known as St. Venant's Principle, and we kind of bandy this around, but it's all about this critical diffusion length and getting away from that region of local influence for different kind of purposes. Now, I've used one significant length in my particular case, and we can see that typically we would use 2 to 3 significant lengths. Now, what is that significant length or significant distance? It tends to be a geometric feature. Here we've got the width of the plate. We're going to see very shortly. We actually can look at the diameter of, say, a shaft. When a little bit later on, we're also going to look at the length of a feature or the distance of a notch or length of a notch. So significant lengths can be geometric features such as widths or diameters, or they can be quite an abstract length. If you've got an unusual looking component and you're kind of working with that and variations on that, you might well become aware of some characteristic length which is a little bit more abstract, some geometric definition or dimension which is playing a role in your particular case. And as you get experience, you kind of jump on that and say, well, I know this is a key dimension in here. So that's basically the broad conclusions coming from that. Now here's an example. We're going to go to a shaft, and this is an awkward, very awkward piece of geometry that we came across, and it's a long needle-like shaft. And the trouble with it is, if I've got, say, a tip load which is bending this shaft in here, this needle, then to try and keep the aspect ratio maintained, I can only put a few elements in here because I'm wasting a huge amount of elements around here away from the region of interest. I'm assuming the region of interest is here, is here, is here. And I haven't got a very good mesh distribution through there. I just can't get the element count up if I want to keep the aspect ratio sensible. So I've got about a 1/4 of an inch diameter in that particular case, and that's of the major diameter at this joint. So that's this diameter over here. I'm using that as my call for the characteristic dimension. I could have used the narrow one, but this is, again, it's up to us. We're in control. We decide what we're going to use as this dimension here. Now, what I want to do is to say, let's get a local model. And what I'm going to do is chop out a section 1 inch upstream, 1 inch downstream from that particular section there. And I attack the boundary conditions this way. The left-hand boundary condition, I'm going to just apply a constraint to ground. The right-hand boundary condition, I'm going to use a rigid spider element, and this is a typical spider element here, and I'm going to transpose that load balance from that far point, bring the shear force to that point, and then the corresponding moment to that point as well. So I'm going to do a little short section. And the bottom picture here is the short section. And what I've done then is to say the spider gets the load in, both the moment and the shear force. Now, there's a couple of things going on here. If I constrain that left-hand end, it's over-constrained because I'm locking it down. I'm not allowing Poisson's ratio effect to naturally allow changing that cross-section. I'm locking it down at that particular point, as opposed to being locked down over here. So that's one issue, and that's, again, now our constraint boundary condition. Use some Venant's theorem to get far enough away from the region of interest. Similarly, with the loads being applied, well, again, I'm applying point loads, and I've got this rigid element. So I've got poor local stresses immediately in. I've used the term RBE2. It's a perfectly rigid element in here. It's a displacement relationship type of element. And the little perturbations or stresses in here, it'd be a bit of a mess if I looked locally in there. So I want to get a diffusion out. So my critical section over here doesn't know really where it's sitting. it sees the boundary conditions, it sees the influence we diffuse out. So just as a comparison, this is the full model, poor element distribution, just because the sheer number, I've zoomed in here. This is the actual complete model in here, and I can go to town more. I can use that element budget. Instead of wasting elements down here and down here, I can pump them in where I want to see the local elements. So a great application, really, of St. Venant's principle. Now I actually play a little bit of a game here, and I say, well, that's what I started off with. How tight can I make this? Because again, element count is everything. So 4 diameters I'm using in here, so a factor of 4 on that dimension. I get very good relationship to just a simple calculation. The stress varies slightly because the mesh is changing in here. I didn't do a real convergent study on the mesh in here. It was more the nominal stress I was interested in, and the simple stress concentration. I then shortened it further. I get very similar stresses between these two. So going to, I've got to move my little picture out of the way, 2 diameters in that particular case, I'm still in good shape. Now I push this a little bit further, and 1 diameter, I'm starting to get the influence of the boundary condition here and the loading in here starting to influence the stress picture in here. So that 1 diameter in my particular case isn't enough. There's not enough diffusion length going on in here. So I can relate that back to the plate and everything else. We could do a real kind of study on the detail of the stresses in here. Come down to 1/2 a diameter, and I've really, I really messed it up. The influence of the loading, you can see the patterning in here. The boundary condition here is dominating the stress diffusion. The assumptions or the limitations of the rigid element here, again, the same kind of idea. So basically, I've really disturbed the local stress variation because I'm not kind of following the principles or the guidance of St. Venant's Principle. So again, you perhaps would have to explore this, get familiar with it, and once you've got some experience, then you'll have more idea of what kind of that critical length should be. This one is a little bit of a flyer here. I'm going to talk about geometry features. So this is a model I knocked up fairly, in fact, yesterday. So it's not kind of fully bottomed out. But the idea is that I want to have an I-beam, which is going to be representing a plate which is loaded in the middle and built in at both ends. Now, I've used a symmetry plane here to establish that. I've loaded the face here, and I fully fixed the end here. I didn't want to actually hardwire this to ground. I wanted to see some diffusion of the end in there. So that's the idea behind this little model here. So I've got a model which actually doesn't have a bracket and doesn't have a little, I'm assuming a fillet weld and a weld toe in there. This one here, if I can pick up my arrow, this one has a bracket or a gusset and also has a little weld toe in there. And this is a classic little problem, and when we're dealing with stress concentrations, particularly with welds and things like that. And the maritime certification authorities, DAS, Nord, Veritas, Lloyds, and so on, they actually use this as a little case study to use what they call the hotspot approach, which is basically say, can we eliminate the local stress concentration there? Because in a weld, it's a specific locked-in profile. I put a little radius in here. That's too locked in. We want to have a generic application. So what they do is they want to get rid of that stress concentration factor there, actually extrapolate the stresses through, and then say, well, with the nominal stress back in again, let's apply a stress concentration factor which we bring from our practice and our principles, rather than getting stuck with whatever that comes from FEA. So I've kind of jumped on this idea to say, well, we've got a sort of some Venants Principle idea here coming from the weld toe, but also from the bracket as well. As we move away from the bracket, maybe this beam doesn't care about the influence of the bracket. As we get closer in, maybe the stress distribution here doesn't care about the influence of the weld toe if we're far enough away. So to my mind, it's like an extension of St. Venant's Principle. Here are the stress and displacement results for the two. I've clipped the same at stress levels, which are stress levels which kind of characterize the bending at the center here. We've got peak bending here, then reversal of bending as we come down to the root, and we also have a stress concentration at the toe there. So that's basically the idea. So I'm going to drill down a little bit, see the difference between these two. And just a quick review, this is what DNV, ABS, Lloyd's hotspot methods kind of apply. And so there's my bracket, there's the well toe. And what they're saying is there's a region 3 in this beam far enough away from the bracket where the stresses don't know anything about the bracket. They haven't got that stress diffusion influence yet from the bracket. So that's region 3 outside here. Region 2 starts to see the influence of the bracket, and it's only region 1 that starts to see the influence of the well toe. So based on that, what they're saying is if we take the stresses which are present in region 3 and 2, and we want to get rid of the influence of the local disturbance of the well toe, then we can extrapolate through, and we've actually extrapolated this region, and then we get back to a nominal stress. So I kind of jumped on this idea. It's really like an application of St. Venant's type of principle, where the disturbance is a geometric feature rather than a loading feature. So this is what I've come up with here. So this is the stresses now in the extreme fiber. So here we've got to kind of remind ourselves, there's the end plate and there's the beam. And we're looking at stresses kind of running along there from left to right. So looking at the stresses, we get, this is the root bending moment here. This is without the gusset. So I get a root bending moment here, and then I get a tip bending moment here. Now, because it's constrained, it's basically a center section here, then we get actually a reversal of bending. So we get a reversal of the bending stresses. So if I draw the center line on here, that represents the extreme fiber stress top and bottom at that station due to the root bending, and the reversal of bending somewhere around here due to the center line. Now, with the bracket, it's kind of interesting. The bracket or the gusset actually, because of the way I've loaded this, it changes the bending moment down in here. So because actually we get the influence of the gusset there, the actual line of action of the bending moment coming out here, the loads coming out here, puts a slightly different bending distribution into the beam. So I can't quite compare apples with apples there, but nevertheless, if I take that account into effect, you can still see the same kind of idea. So yes, we get a slightly more different bending distribution. So the root bending is slightly different, and the center section bending moment is slightly different. Hence, the stress levels change slightly, but nevertheless, we can see a couple of things going on here. This is the local gusset influence. So this stresses here are happily coming down under the boundary conditions implied by the bending moment, the root bending moment, and the center section bending moment here. And then you can see this kind of at the top and the bottom, this global change in stress is the gusset influence. So yes, there's like a St. Venant's principle effect, and it's a little bit longer than the gusset length. It extends a little bit forward. This is the gusset length because there's the well toe there. So about maybe 1.5 to 2 times the length of the bracket. Away from that, the beam doesn't care. There's no local stress influence on there. The blip here is the local stress raise of the well toe, and this is where we get our particular, it's not a singularity, it actually would be a converged stress as long as I did a good job in here. You see that's the stress concentration factor. It's about a factor of 3 in there, just eyeballing it. So that is very much a local kind of influence. So again, it's kind of summarizing the way that the DNV and the ABS and Lloyd's register are kind of thinking about things. It's a local disturbance. So again, I think it's a useful interpretation of St. Venant's theorem there. So in summary, the St. Venant's principle describes stress diffusion due to loading. That's the fundamental principle. But we can extend that to constraints, but also to geometric features, which I think is interesting. The bracket influence zone is the same order as the bracket length, maybe 1.5, maybe 2 times it. The well influence zone is actually very much the same as the well toe width. So there's very local disturbance over there. So I kind of put that out as just some general thoughts and some general observations. So we looked at the definition of St. Venant's principle, extended it to constraints as well as loadings, and then a bit more unusually, I think I've also said it can be applied to geometric features. So again, I'm interested to see what experience you guys have with that, any recommendations, any favorite methods, any kind of comments, albeit criticisms or whatever it might be. During my 12 years of doing e-learning, I've learned to have a very thick skin, and if you disagree with some of the comments and ideas and so on, then it all adds to the discussion. So I think just as a closing note, thanks very much from my side for watching this. We're going to be getting into Q&A now. I just run over slightly the half hour. And just a little bit of a heads up for the next session. That's going to be talking about FEA sanity checks. And basically, we don't make sure we don't fall into the garbage in, garbage out. But I won't be talking about full kind of project checking. What I'm very interested in is those quick checks within about 5 minutes of seeing the results coming out the model. Are we on the right ballpark? Is the model rubbish? Do we stop at that point and redo it? Heading off here, the idea that I don't want to spend, say, 2 days post-processing and producing a report on results which are rubbish, and I could have headed that out early on. So we'll have some ideas in there for the next session. We'll post the timing. I think we're going to probably settle down to this same time, but again, we'll get confirmation of that over the next couple of days. Look out on LinkedIn in particular, and I also on David's email blasts, and generally just kind of keep an eye open for what David has called Talking Shop with Tony Abbey. Okay, that's me done. I'll head over to you, David, now. I'll hand over to you, David, to go into the Q&A sessions.
Thanks very much, Tony. Yeah, Talking Shop with Tony Abbey. We like alliteration at NAFEMS. It would have been better if it was on a Tuesday. Tuesday's Talking Shop with Tony Abbey. But, you know. We do have a few questions that have come in. Thanks, guys, for getting those across to us. I don't know if you can see them on the right-hand side of the screen, Tony.
So Harasharaj says, what alternative method do you suggest instead of the RBE2? You can use a flexible spider element for the loading side, so that would be an RBE3 type. That's probably the best approach to use. Either of those would work because we've got a fairly stiff cross-section there. Or you could, if you've got an interface which allows you to apply loading to the face, then you could apply loading to that face. It's just more convenient very often to actually load through a spider, because you can see more explicitly what's going on in there. Mike says, the fillet in your needle shaft or I-beam example, assuming the load was cyclic, do we use the peak reported stress or mesh discretization cause an inappropriately high stress? Do we need to refine the mesh until we settle on a consistent stress? Yes, Mike, that would be a good second stage. So I guess first stage would be to see if we got sufficient diffusion length, and we're really looking for the shorter the better. Then our local model is kind of like the best, is like the leanest and meanest. Once we got to that stage, then we can throw elements at that. And basically what I would do then is to put as many elements as I could to within the limits of my machine, and then try and get that fillet radius in particular of that shoulder, trying to get that to converge from a stress convergence exercise. So the first approach, really, the Venants idea is to say that our element budget, which is perhaps a limit of our machine, let's put those elements where it counts around the shoulder region. And yes, exactly, Mike. I didn't go on and do a mesh convergence study, but that would be the next stage. Josh Hammer says, hi Josh, do you have any comments on purposely using stress diffusers to lower stress concentrations? For example, smaller holes in each side of a hole cause lower stress concentration at a center hole. Yeah, I kind of thought about talking about that. That's a great idea. What we can do is, and I think I might actually do a little session on this. We've got a plate with a hole in it, and if it's a wide plate, we're stuck with a stress concentration factor of 3. What's very interesting is we can actually put a hole upstream and downstream, and what that does is, again, it's like kind of thinking of fluid flow. If the flow is flowing in this direction, what it's doing is it's kind of warning that that hole, the major hole here, that the stress is now going to be, we put a hole upstream, so now the stress is starting to change, starting to flow, so it's already flowing in a beneficial way by the time it actually gets to the feature that we're interested in. So we kind of get a stress flow which has already been kind of perturbed a little bit, and then it's going to be perturbed a little bit more as we kind of go around here. So it's a kind of the same idea as my being entrained by the wall. As the wall gets closer, all these kind of features are very can be very beneficial. So again, the Venants principle would come in here by basically saying, well, how if I move that too far upstream, I lose that beneficial influence. So that's perhaps where you were going with that one, Josh. You're too far away, we lose the influence. Too close, maybe we get an abrupt influence. So again, there's a kind of critical length there. It kind of all comes down to this Venants kind of theorem that we're talking about here. So again, thanks, Josh, for that. Roberto asks, anything to be aware of about some Venants principle while using a solid mesh model? We talked about the mesh convergence. We tend to have, we're pushed up against it to getting good mesh distribution or fine enough mesh in complex solid models. I would make the point there, I dealt with this needle and the shoulder, and I think that's really where you want to explore your own features. I've come up with about 2 diameters, 3 diameters, 4 diameters is good for that shoulder. That's a rough kind of idea. 4 or 5 critical dimensions usually works, but again, check it out on particular geometry you've got. And again, it is really rather an abstract idea. There's some kind of characteristic dimension. We're trying to get a handle on that. As you play around, as you get experience with different geometric forms, then I think you'll gradually get a better kind of feel for what these might be. It's, again, a little bit of an art rather than more of a science, I'd say. Akshay says, is the principle still valid if the load type is cyclic or for fatigue testing? Yes, it is, because we're going to be using our peak stress as as a stress amplitude, let's say in high cycle fatigue or low cycle fatigue. So that is still very relevant. Everything we're doing here is very relevant for fatigue analysis. Same structure, different loading, different characteristic length, coming from Saravan. No, what we're actually finding is from the plate, the characteristic lengths, if we're thinking about point loads compared to distributed load, or I played around with 2 points, 3 points, and so on, seemed to be the characteristic length was more of a characteristic geometry effect rather than a particular loading form. Now, that would be different perhaps if we got, take the shoulder, that was a bending stress diffusion. Maybe that's going to change compared to an axial or torsional. Again, that's something to kind of explore. But I think it looks like it's maybe torsion is different from bending. I haven't checked that out. But again, I think that the same kind of principle applies there. David Turner says, I like the idea of the hotspot example. This technique has made its way into many common standards now. Yes, I first came across it with Destin and Veritas working on a particular project for them, a sort of maritime certification. The idea of the hotspot method, the local disturbance, I think is becoming quite a common approach. Is actually also similar in many ways to the linearization, the stress linearization, like the ASME stress linearization. There we're more going through thickness rather than across the surface. But there are, again, great parallels in there. There, they're actually taking account a little bit of the actual influence of the stresses locally and kind of juggling that linearization around, but it's still the same kind of idea there. There's an interesting question from Neil. So DMV, etc., recommends particular element sizes and types for evaluating hotspot stresses in offshore structures. Rather than applying this approach, one might just as well increase the mesh density for a converged stress calculation. That's a very interesting point, Niels. I've always felt that those particular sizes and pickup points are more harking back to the days when we could only put a couple of elements through thickness, and therefore the positioning of those elements was kind of was quite critical. These days, what I would say is I tend to just saturate the mesh, look at the curves as I've done, look at the stress distribution curves, and then extrapolate using either eyeball or some sort of more formal method to kind of extrapolate from sort of like the zone 2, zone 3, zone 2 into zone 1. I don't think we'd be restricted these days to the very formulaic distances that are recommended by those guys. I think that harks back to the old days, as I said, with very coarse meshes. Psycho makes a comment: when using part of the deck, presumably for offshore work, for maritime work, we use 1 meter of deck around the affected area of the deck. That's interesting. So I guess you've got a particular size of bulkhead, deck region, and so on, and so 1 meter is what you're using. It'd be very interesting to see how that compares to the actual dimensions of the deck. So if we could sort of say, okay, 1 meter, does that relate to anything typical physically? But that's an interesting observation there. Lewis asks, why use tetes rather than meshing with bricks, where it's easier to control the aspect ratio of the elements? That's a perennial question. You've got to sort of prepare the geometry ready to hex mesh. Just for speed, I can fill this, if you like, fill this geometry of the beam easily with tet meshes. Again, that's a big question. Maybe we'll pick that up on another presentation. JB asked a question: the way you distributed the nodal loads in your example suggests the underlying assumptions of consistent nodal loading. Could you remind everyone what the key features of the integral equation for consistent nodal loading are? Basically, the idea is that if we want to put nodal loading on, we want the preprocessor to do that for us. We just say this is the distributed loading we want to apply, and then the preprocessor goes and figures it out. Or the solver might figure it out if we say it's a distributed load. Basically, we're using the shape functions of the element to say that we want to have a consistent work done. So basically, if you like, the distributed stress times the strain we're trying to achieve, the work done there should balance the individual point forces we're applying to the nodes times those nodal displacements. And for mid-side nodes, for example, sometimes we get very strange nodal loading patterns that come in. Again, a big topic, maybe something we'll expand on a little bit later, but I just simply said the corner nodes, which have half the stiffness, have half the load applied. That's the beginning of the overall principle that the JB is alluding to there. Again, it's called a kinematically equivalent loading. Again, the shape functions, the work done by the shape functions, giving us the stresses and the strains, should be equal to our somewhat clunky nodal loads and nodal displacements. And that's basically the idea behind there. That's why we get these strange ideas, such as half the load at the free edge. Jaya Pragash asks, does the behavior change when we change the magnitude of loading along the width of the plate? I mean, is there a formula to understand which loading pattern across the width of the plate can achieve the maximum stress flow? The best one is if we're trying to achieve a consistent stress and we put an even distribution of stress through there. Putting a point force in is generating a singularity. If I put a little spread of load, it's getting better. So we can really think of the point load as being one extreme. It is a singularity, but it's diffusing out. The distributed load is the best shot. And somewhere in between there, we may end up with some sort of compromises. There are equations to talk about the power of the singularity. If I put distributed load across, say, half the width, the center line, where we run out of that distributed load, there is a weaker singularity there, and there are some equations and so on to kind of describe the power of those singularities. Schmidt says, very interesting, Tony, what happens when the load is applied at some angle from the plate length direction, say 30 degrees off from the x-axis? Then we'd have a diffusion due to axial load, and then also a diffusion due to bending and shear. So that would be an interesting thing to try, and it would be interesting to say, if that's the case, is it still the same driving characteristic width of the plate in my particular case? Do we get the same effect? Interesting idea, and that might be something I kind of try, and maybe sort of those of you working from home, you might want to try that as well. Again, it comes down to trying to put my handle on a characteristic length or feature size dependent on the different forms of loading. And it's the forms of loading, such as here, axial versus shear and bending, that would I be interested in. Not so much the form of the, is it a point load or is it a distributed load? That's an interesting question. Mira asks, can you please elaborate on stress concentration factor of finite plate versus infinite plate of the center hole? What practical scenarios do you utilize both and the selection criteria? Again, it's a plate with a hole in it is perhaps a rather boring example, but it's a very good example. The point I was making there, here's a plate. We're going to apply an axial load to that. We assume we constrain it on that side. If the plate is wide enough, or the hole is small enough, then we can approach a stress concentration factor of 3. So let's say we've got a tiny little hole in there, because basically it's a disruption of flow is the way I always kind of describe it. The stress is flowing along here, suddenly sees that and has to flow around here, and it gets perturbed kind of like in a big way, and that perturbance field kind of goes out kind of quite some way. Now, if we change that and say now we've got a plate and we have a larger hole, that's one way of doing it, the stress concentration factor actually drops. And the reason here is that typically KT over here is going to be around about 3, roughly, as we get towards an infinite plate. KT is 3. So that's the peak stress compared to the net section stress or the nominal stress. Here, KT could be just as a flyer, maybe 2.1, or even, let's call it 2. It's dropped down a bit. Now, why would that be? Well, because it comes down to this idea of the stress diffusion or the stress flow. Now, the stresses which were out here, if I kind of can point to this, change color, stresses which were out here, which were having to change abruptly, if we take that same stress line now, that stress line at that distance, if you like, from the edge of the plate, is now actually being constrained to move parallel to the plate. So if I draw that and then move it up a bit, that guy that was disrupted is now entrained to move parallel to the plate. This guy is the one that has to get disturbed. So we've got less disturbance, if you like. So if we think of like fluid flow, we talk about pressure drops and so on, and stream velocities, then the velocity goes up here more, and the pressure drop is more than this guy over here. So our effective stress concentration factor is dropping, and in the limit, if we only had a tiny little kind of distance away from the hole, which is like here, and we put an edge right on here, then surprisingly, the stress concentration factor would go right down, because we're pretty well forcing the stress to flow down that ligament almost like an even flow. Now, the kicker is that the nominal stress, which is our load divided by the net section, that's going up all the time. So although I have a stress concentration factor here, say of only and again, I'm just guessing numbers, let's say it drops down to right down to say 1.2, but it's like 1.2 times a very big nominal stress versus a 3 times a much smaller nominal stress. So it's actually like two things going on. It's like a double-edged sword. Your stress concentration factor goes down, the example we have at the right, but the nominal stress goes up. So it's again a very interesting kind of effect there. And aligns to the previous question on can we actually put holes and features in a sympathetic way? Yes, we can. So there's all sorts of interesting things we can do to juggle to try and get that stress flow to be an optimum. Karma says, some Venants principle is used in submodeling techniques, which is what we had essentially with that needle. And then he makes a comment, one tricky part is deciding the boundaries of the submodel so we don't get the boundary effect. Yes, exactly. Do you have any tips on how to decide the proper boundaries of the submodel? So it's a distance thing. So that's really what we're trying to do. For the needle there, I came up with probably about I think about 3 diameters looked safe, looked okay. I had that kind of study where I kind of came right into half a diameter. There, the influences were bad, and they were really wrecking the value of the results. As I spread it out, we got to that kind of critical length. If you go too far, you're not doing any harm. You're just kind of wasting elements. So the judgment call is basically you're trying to get the elements where they want to be. So for the submodeling, we want to get a shorter submodel as possible. So yeah, and again, it's a bit of an art rather than a science. So I wouldn't want to say exactly 2, 3, whatever the value is. That's something you've got to kind of explore a little bit. Ivor makes the comment, fillet radii we use on our small-scale flexing devices is about 1.5 to 2 times the thickness or diameter. So there Ivor's been exploring this, working with it, and he's come up with a characteristic dimension. And that's very typical once you're in a particular industry, a particular type of structure. This is what you're going to kind of come out of it. So we can give some general guidelines, general ideas, but again, your experience is going to dictate what you think is going to be there. So John makes the comment on the cut needle model. Was it fully constrained axially? So it's over constrained compared to the longer original. I prefer to partition the model and have the coarse mesh at the left-hand end, either that or use the results from the coarse mesh at the cut plane. Yes, you're right there, John. What happened is that I sometimes describe this as elephant's footing. I'll explain that. That left-hand end, as you say, is over-constrained, and I made that point in the slides, because I'm locking down the constraints in that region. I'm not allowing Poisson's ratio effect to contract the cross-section, which it would do naturally if this is actually sitting at a point down the shaft or the needle. And the elephant's footing is a phrase we use because what happens is we lock that dimension in. This dimension wants to shrink naturally. So what tends to happen is we get a section which looks something, if I can sketch it, looks something like this. It kind of runs in and then it kind of expands out. So this is like a sideways view of an elephant's foot, if you can imagine that. Yes, we inhibit the natural tendency for this end to want to shrink. My argument there, John, is that I'm far enough away with my St. Venants effect theorem, principle playing a role that basically that diffusion length there, that's the local effect, let's say there, 1 diameter. I've come further than 1 diameter away. I'm looking at stresses kind of upstream here. I'm looking at stresses over here and to the right of that. So my argument is that yes, that is a local effect, but by the time I get here, that effect has diffused, so there isn't an issue with that. That's the argument that I would be applying there. It would be interesting to see the effect on mode shapes and vibration stresses. That's coming from Radii. That is another interesting idea. Dynamic analysis takes 2 stages. There's the accuracy of the mode shapes, the fundamental responses, and that's one issue. And then if we are then using, let's say, a modal method to establish stresses at a particular time point, using a combination of those mode shapes, that's a different question. So I think the question probably plays more to recovering stresses once we've got our dynamic results coming out. And then everything we talked about statically is also true dynamically. In dynamics with normal modes, sometimes what we find is that local features are not important because the mode shapes are not influenced by that. One example I'm thinking of here is on the dynamics training course, what we have is like a sine gantry which has a base, a tall pillar, and then a horizontal member coming across here. And what we find in that particular case is that how we constrain the base is actually not important, whether we actually put, say, like 4 bolts or fully built it in, until we get a certain frequency content. Lower frequency content, say, subject to seismic analysis, the base really doesn't care how it's constrained because most of the action is associated with the flexibility and mass distribution of these arms here. As we get to higher frequency content, then the base starts to play a role there. So it's a little bit more subtle when we're coming to dynamics, and I think it's the fundamental modal influence, what the modes are doing, and then they combine it together, and also the stress distribution when we actually turn that into like a frozen stress plot. So again, a pretty big question there. Chun says, Tony, does the principle apply to high-speed events such as crash? A very, very good question. I would say we'd have to be very, very careful, because with crash, we get local stress concentrations. They then will start to go plastic. We're forming plastic hinges, and our configuration starts to change. So it may well be that we can't ignore that, because that's what's actually prompting the configuration change, the load path change, and so on. So in an impact crash study, any kind of nonlinear analysis like that are actually looking at these local hotspots, and they may be not just staying local, they may actually influencing the change of the overall response. Niels makes a point: the characteristic length might very well related to the resisting dimension, i.e. to the width and height for axial stress. This indicates that the shear part will be related to width and height, and bending will be related to width squared. That's a very interesting idea, Niels. It might be something I pick up and try, and again recommend other people might want to try that out. So you're going to have a different result whether we are applying axial load or bending. That's a very interesting point there. I don't have enough experience to be able to kind of pin it down. Trying the plate was the first time I really tried to kind of expose it and say what's going on in here. So to take that plate and extend it to bending and to shear would be a very interesting kind of approach. Lewis says, can the Venant principle be used to approximate the length of influence of a stress concentration feature? Absolutely. That's kind of what I was trying to kind of suggest with the both the needle really and also the beam with the gusset and the weld toe. That's how I like to do it. I kind of stretching some Venants to say, let's look at this geometric effect, essentially the stress concentration feature, which I call like a geometric effect. So yes, I think so. Probably that's not that is where things are going to vary, depend on the nature of features and the nature of the geometry, stress concentration. But again, we're probably with some experience with particular types of features, we could get to settle down, as somebody was mentioning. I think I was mentioning a particular dimension. Somebody else was mentioning dimensions of decks. As we start to get more experience with our particular structures, I think we can start to put that in as something we can handle. And as a general comment there, what I'd say is that I try and do, when I do a study like this, I try and write a little internal report, and I try and use that report in my project work. So I might say, I'm using this approach because this is what I found, and then I relate back to my own little internal report. So I kind of building up confidence in particular methodologies. So that might be an approach you might want to take. I think we probably need to call it a halt to it there. But I really do appreciate all the comments coming through, and really appreciate the support. It's been absolutely tremendous. So I'll try and get a digest of these questions, and in some form, we're kind of thinking as we go along. We're making up things as we go along. We try and put that digest out in some kind of form. So I'm going to hand back to David at this point. David perhaps has some further ideas on how we might progress. Matt might do as well. And so over to you, David.
Yep, absolutely. Thanks very much, Tony, and thank you guys very much for all your questions. As Tony said, this, we pulled this together in response to try and make people feel part of the community and still feel connected. So thanks for Tony for giving up his time to do this today, and thank you guys for coming along. We will be developing this over the next few weeks, I think. Like Tony says, maybe getting the slides out there, getting recordings out, which we'll hopefully be able to do via YouTube and LinkedIn over the next few days. So you will get access to that. We'll try and keep you all up to date as to what's happening with the next episode and with the recordings and things here. I've taken a snapshot, Tony, of the Q&A, so I would imagine Tony will be delighted to continue that conversation over on his LinkedIn page. So if you do have any questions on today's content, that would be great. Get over there. But yeah, I guess it just falls to me to say to everyone, thanks for coming along. Thanks for supporting the initiative. We hope to see you again, probably next week, probably at the same time. We'll let everyone know. As we've said, it's very much a movable feast at the moment. But thank you very much. Hope you all have a good weekend and stay safe. Bye for now.
Thanks a lot. Bye-bye.